0606 for angles. Use soft keys for tool 0606, set speed to 300, and clear extra data. Note, threading tool. And M50X2 details. Find the turning cycle with soft keys. Let's pick up the piece we saw last time and add some operations too. Complete what we can. Call the turning phase. My idea is to add a 50 pitch thread in this area for a useful length of 10 mm. So, as a first step, let's go to our tool, offsets, and see if we have a suitable threading tool already entered in the table. Here, in position 6, we have a thread cutter, and it's exactly in the position for external threading. Another thing the machine asks for is the opening angles of our tool. So let's remember T606. Let's go to our soft keys related to the manual guide with the fixed format and input a turning tool, which we said is 0606. Let's change the cutting parameters to fixed speeds of 300. And let's delete, as always, the extra data that our fixed format has inserted. As I taught you at the beginning of these tutorials, I preach well, but practice poorly. Please, when you're in the workshop, don't forget to take notes and make them clearer for the next person. So here we could write threading tool, and then below we could, for example, add other data like external threading M50X2, type of insert, brand of insert, so that whoever has to set up the machine after us will have more information available. As we proceed in this particular section to ensure clarity and precision for the benefit of future users, as a reminder to enhance understanding and facilitate ease of use in our operations, to maintain consistency and accuracy in our documentation for optimal performance and efficiency in the workshop environment, to support seamless transitions between different operators and ensure smooth workflow throughout the process as we continue to develop our skills and improve our techniques in machining and threading operations for better results and enhanced productivity in our daily tasks and responsibilities within the workshop, to achieve our goals and meet our objectives in a timely manner and with precision and attention to detail as we strive for excellence in all our endeavors. Let's go back to our soft keys for the cycle and look for the cycle that interests us. Turning cycle, no groove turning, no threading. It's very simple. It divides into external threading and internal threading. Let's select external threading and see what it asks us. The cutting method refers to the classic cutting methods that you can choose based on your preferences or the preferences indicated by the tool manufacturer or the type of material you're working with. In this case, we choose one over the other and move on to the threading direction, which in this case goes from Z plus to Z minus, so the threading direction is Z minus. Finishing allowance, meaning the allowance that I leave after roughing out the entire thread before finishing it with 2 finishing passes, which is an important factor in machining processes. The type of machining means you want to set a pre-established cutting depth, or you want to set a pre-established number of cutting passes. Remember that the number of cutting passes is a numerical value, so 10. While the depth is a real measurement that should be expressed in millimeters, so obviously not 200 but 0.1 for example. So I want 10 passes. I send it and my thread will be made in 10 passes. Approaching, I get closer by moving 2 axes simultaneously. Safety distance. So when I get closer, if I'm going to do an M50, I'll go to M51. For the safety distances on entry, we have a pitch of 2. So let's add at least 1 millimeter more than the pitch. It's always better to start with even twice the pitch of the threading. Safety distance on exit is 2 millimeter. Direction, X. That is, we are obviously working in external threading from X plus to X minus. Let's insert it. The machine automatically takes me to the figure menu. What type of threading do we want to do? We can do a gas thread, a unified thread, a metric thread, and a general thread, where I have more generic data. We have the metric thread. Let's select it. We already know that we need to do an external one, and we already know that the external diameter is 50. Point of the thread is 0 because it starts from here. If I had threaded this diameter, I would have put a -15 step of the thread to me. Useful length. The useful length that we want to thread plus the 2 m of exit. So 10 m depth of the thread. Be careful. Let's delete this measurement for a moment, or rather, let's put the wrong 0.1. So the depth of the thread, gosh, I don't know, but the machine knows that the diameter is 50. The pitch is 2, and we're talking metric. It calculates it for me with this soft key. Honestly, I've always left it like this, okay? It tells you the thread number, the distance between the crests. You always leave the threads and the number of threads instead of the number of principles. And here we have only one principle, so we enter our code. Let's simulate it and see what happens. So we can take the whole previous part. We could even start halfway, but the graph wouldn't be updated. And here we have our 10 passes of threading. For example, I hate the threading macro with the manual guide. It's extremely easy. Now I would say let's go ahead and make these 4 holes at the bottom of our panel. Here we no longer need to work on these soft keys, which are the turning soft keys, but we need to move and work on the soft keys for powered tools, so essentially for milling. Also here we have the fixed format, but we have a problem. The fixed format in the simulator hasn't been properly filled out, and I still haven't figured out how to enter the fixed formats in this simulator. Here too we have the fixed format, but we have a problem. The fixed format in the simulator hasn't been properly filled out. In my workshop machine I used a soft key to create formats. Here we lack that. I need a 10 mm bit in a horizontal position. Let's check tool, offset 13's geometry. In the machine I had in the workshop, which was quite advanced and efficient, I would open a fixed format, which was pre-configured, and there was a soft key conveniently enabled to create it, so I could easily create a decent fixed format. Here, unfortunately, we don't have that feature, so for milling operations, we need to manually and carefully enter the first parameters. I specifically need a 10 mm bit, positioned horizontally. And here, fortunately, we have such a bit available. Let's thoroughly check the geometry for tool offset 13, which we assign. So, radius 5, diameter 10. Perfect. The T13 is our tool. Let's close that and manually input M35, G28, H0, which are the data related to enabling the powered tools, and zeroing the C-axis, T13, T13, G97 fixed speed, 600, M13, EOV, insert. The more attentive among you may have noticed that in the earlier tutorials I started the powered tools with M3, P12 and the self-centering tool with M3, P11. Now, however, I simply use M3 and M13 for the powered tools just because P11 and P12 are mainly related to docent machines, while 13, 3, 4 or 14 are linked to other types of machines, like this software, which is related, for example, to MCO. It's about following the guidelines given to you by the person selling you the machine during the installation phase. Those are 2 simple things that you just need to remember. Let's go back to the milling soft keys and set a cycle. We want to drill, so let's start Drilling. What do we want to drill? We want to drill for a length, so we'll start 2 minutes away from the flange, drill 10 meter and then retract by 3, making a total length of 15 meter. I set the pass depth to 15. If I had set it to 5, it wouldn't have drilled for 5 millimeters. Instead, it would have executed the chip breaking cycle every 5 millimeters. Overload entity. Here we basically tell it whether we want to provide data so that it calculates the tool's exit or not. No, we provide the data in return mode. Go back 1 millimeter more than necessary. Point. What does point I mean? Point J, where the tool will safely position itself before starting. Well, where will it position itself? At Z, minus 88. Here, I'm going to write minus 88. You see 100, minus 10, 2 millimeter of safety, minus 88, enter. The cutting depth needs to be set in the direction. So the minus sign is important. We cut from Z plus to Z minus for a depth, as we mentioned earlier, of 15 mm. Safety distance is 2 mm, feed rate is 0.12, and the dwell time is set. We input that. How does it approach? It will approach by moving X and Z simultaneously and interpolating the Z-axis. Specifically, the machine tells me, do you want to enter more gently compared to the feed rate of 0.12? Do you want to enter more gently? Yes, I want to enter for 2 millimeters at a feed rate of 0.08 per revolution, and I want to exit the last 3 millimeters at 0.08 per revolution. If you don't want to do this, set a value of 1, and replicate the feed rate you entered in this box. We input that, and it tells me, okay, now what do you want to do? We understand that you want to drill, and we understand that you want to drill to that depth, but we don't know if you want to drill along a flange in a concentric manner, randomly along the diameter, or something else. Well, I want to do this, face drilling on the Z-axis. Okay, where is the starting point? The starting point is located, coincidentally, I made a previous detail. You see that you find it already pre-filled. It depends on what I did before. Z90, B90, the X40, 4 holes, diameter 10, radius 40, spindle orientation. X40 is already in place because 4 holes, specifically diameter 10 to diameter 80, therefore radius 40. The angle of the starting point is, in terms of orientation, the orientation of the spindle, approximately. I don't have any other reference point, so I set it to 0. What do I want to do? I want to make 4 holes, spaced 90 degrees. Part. Okay? Put them in. Simulate. Reboot. Start. I'm taking my time, but look, programming like this is really straightforward. Let's see if we didn't make any mistakes. Here we have our threading. 1 hole, 2 holes, 4 holes. There. We go. Done for the completeness of the drawing. Now let's also do the 4 radial holes. So we go back to edit for easier reading and insert a couple of blank lines, slowly and very carefully. Let's specifically discover a drilling bit with a diametric measurement of 6, therefore a radial distance of 3 in our tool adjustment. And correction table. Here we have 14 with a radial distance of 3. Let's see if it's already indeed considered as an existing drilling bit. Yes? Indeed, it is confirmed to be identified as such. It's positioned directly, which means it stands at precisely right angles to the rotational spindle's axis of rotation. So that's good news. Let's shut that down now, completely. We said we need to input this particular set of information by ourselves, manually. So let's go here. Create what is known as pairing. Choose carefully those 4 lines we're concerned about, and then proceed further by inserting them accordingly into place. To be truthful though, honestly speaking, we could technically omit these 2, but still find value reiterating them nonetheless, just in case they prove useful later on. Now let's record, accurately stating 14, 14, alter respectively. Now we're going forward towards introducing our operational cycle. Oh, sorry, I just recognized I used entirely incorrect program, because cycles tend naturally alter over time. Drilling cycle depth cut specification follows next. So beginning from initial point where there's diametric measure starting at 60, reaching 32, henceforth these let us state simply 30 millimeters instead. Radial measure calculated being 60 minus 30 divided evenly results 15, yet also considering minimum exit. Entry points are just 20 ultimately. All of this corresponds to what was said earlier, while J, in this case, becomes a diametrical measurement. Start drilling from 62 millimeters. Radial depth 32, works perfectly. Cutting depth minus 20 for distance, feed rate 12, all good. Toolum at 0.08, now want lateral drilling. We said that we make the cutting depth equal to the cut, so minus 20. Distance and safety is 2, feed rate is 12, pause duration is 1, everything looks good. In particular, I'm using the same parameters as before, 2 millimeters at 0.08, then I re-engage at 0.12, and the last 3 millimeters at 0.08. I'll insert that. And what I want to do now is not this anymore. I want to do a lateral drilling. Axis C, along the diameter. Perfect. B becomes the diameter. Okay. That's the exact point where the tip will start working. Minus 70, what is it? It's the Z, that is, you see 130. Difference from 0, 70 meter minus 70. Starting angle, 0. 370 starting angle. Starting angle, starting angle. Angle, starting angle, angle in. In fact, 2 holes, a line. Later, maybe here we'll make a small adjustment and see how changing the starting angle affects things. Here we also have 4 repetitions, 90 degrees. Insert, and it's done. Simulate, restart, start. The 4 holes align, so I'll change the angle to 45. Simulate, restart, start. Planned a hexagon, but video is long, so next time. Now staggered at 45 degrees. Reference was 0. Modify here, do 0. Alter to revert. Threaded and drilled quickly with few blocks. Programmed threading and motorized holes efficiently. To see in order. Modify repetitions and set. But I set it to 45 and let's see what happens. Simulate, restart, start. I intended to do a hexagon as well, but the video is already long enough, so we'll do that another time. Otherwise it really becomes too much. You see that now they are staggered at 45 degrees. We had a reference, we set it to 0, and then you also learn to read it. Because look, you just need to modify it here, and there's no need to do anything else. Just do 0 point alter to go back to the previous situation. But what I want to show you is that with just a few blocks, I threaded and drilled in no time. I did all the programming for threading and motorized holes. I'd say it doesn't get better than this. And since we want to see everything in order, I'd also say to go here, modify the repetitions, and set that with just a few blocks, I threaded and drilled in no time. I did all the programming for threading and motorized holes. I'd say it doesn't get better than this. And since we want to see everything in order, I'd also suggest going here to modify the repetitions and set I send the modification, simulate, reinitialize, and then start. And that's how we have our piece really made to design with an added thread. That's it. That's all. You see that we modified the 3 grooves in a flash, referring to the previous video. Well, I hope I was clear enough on a topic that seems really complex, but is actually very easy to manage, like the manual guide, which is truly a great help. Those who will work on Mazak might say Mazak is 1,000 times better, and they are right. But if you have Fanuc, you need to use Fanuc. If you know how to use this, I think you can, then easily learn to use all the conversational programming that exists in the world, because this is very straightforward in the process. Well, if you liked it, I ask you to give me a like, subscribe to the channel, and share my videos on your social media. If you didn't like it, as always, just pretend it didn't happen. Until next time, thank you very much for your attention. Bye-bye.